At its core, a URL shortener has a straightforward job. Take a long, unwieldy web address, map it to a compact 7-character code, redirect the user when they click it, and log the interaction. But that simplicity breaks down when you hit production scale. We are engineering for a target of 100 million new URLs generated every month and 10 billion monthly redirects. This specific traffic volume introduces a severe architectural constraint. For every single time a user creates a new link, the system has to process 100 redirect requests. Despite handling 100 times more read traffic than write traffic, the system operates under a strict latency hardline. Every redirect has to complete in under 50 milliseconds, so the user never notices the hop. At 10 billion monthly requests, a standard database lookup becomes a systemic liability. Engineers must design an architecture that prioritizes read throughput by removing database lookups from the critical path. The first major engineering hurdle is generating trillions of mathematically unique 7-character shortcodes quickly. Looking at this 3-part diagram, the first column shows a common initial approach, taking a long URL and running it through an MD5 hash. Because you only keep the first 7 characters to keep the link short, you inevitably generate identical strings for different URLs, leading to data collisions. The second column illustrates random generation. You create a random 7-character base 62 string, but before saving it, the server has to query the primary database to ensure that exact string doesn't already exist. That synchronous uniqueness check introduces a severe latency penalty on every write. The third column illuminates the optimal solution. Instead of hashing or guessing, you'd use a distributed, globally unique ID generator, like Twitter's Snowflake architecture. This standalone node instantly produces a monotonically increasing 64-bit integer without ever touching a database. You then run a mathematical conversion on that 64-bit integer, translating it directly into a 7-character base 62 alphanumeric code. Because the Snowflake sequence strictly counts upward, the resulting integer and its base 62 translation is guaranteed to be unique. You bypass the need to verify the string in the database. Resolving uniqueness at the algorithmic level allows the system to maintain high-throughput writes without the latency of a database round trip. With the creation side optimized, the focus shifts to the critical path, processing those 10 billion monthly redirects. This system map illustrates the danger. You have a load balancer, an API gateway, and a primary database. If you force that primary relational database to execute a lookup for every single shortcode clicked, you will instantly exhaust its connection pool and crash the cluster. Inserting a high-speed memory store, like Redis, between the API and the database absorbs the read volume. The specific shortcode to long URL mapping is held in RAM, resolving the lookup in single-digit milliseconds. Once the mapping is found, the server has to instruct the browser where to go using an HTTP status code. A 301 status code tells the browser the move is permanent, instructing it to cache the destination locally. A 302 status code indicates a temporary redirect. URL shorteners explicitly use 302 redirects. By instructing the browser not to cache the result, the browser is forced to ping the server on every subsequent click, ensuring the system can accurately log the analytics for every visit. But tracking every click exposes the cache to the hotkey vulnerability. If a single link goes globally viral, millions of users attempt to read the exact same Redis key simultaneously, overwhelming the node holding that key. To mitigate viral spikes, you implement local in-memory caching directly on the application servers. The most frequently accessed links are held in the app server's local memory, allowing it to return the destination without even making a network call to the main Redis cluster. To maximize read throughput, high-frequency data must stay physically distant from the primary database, residing instead in local memory or distributed cache. Because the 302 redirect forces traffic through the server, the application is responsible for tracking rich data on every click, including IP address, user agent, and refer. Focusing on the redirect service node here, you see the paradox. Capturing this dense analytics payload and writing it to a database synchronously blocks the connection, pushing the response time well past our 50-millisecond limit. The solution is strict system decoupling. You insert a message queue, like Kafka, directly into the flow. Now, the redirect service simply fires a lightweight JSON event into the queue. The moment the message is accepted, the service terminates its involvement and immediately executes the fast path redirect for the user. On the consumer side of the queue, background worker nodes pull the batched events. They process the heavy compute tasks, like translating IP addresses into geographic locations, and then write the enriched data to a separate, analytics-optimized database. The architecture accepts eventual consistency on the analytics dashboard to prioritize low latency on the critical redirect path. Storing billions of active URL mappings and click events long-term requires splitting the data across multiple machines. You must shard the core mapping table by a hash of the shortcode itself. Hashing the shortcode ensures the data is distributed perfectly evenly across all servers. More importantly, it guarantees an exact lookup during a live redirect, pointing the request to the specific server holding the record. But a system sharded by shortcode fails the secondary access pattern. When a user opens their personal dashboard to view the performance of all links they've created, the application has to execute an inefficient scatter-gather query across every single database shard to find their records. To resolve the conflict, you duplicate the data into an entirely separate data model. This secondary table is explicitly sharded by the user ID, perfectly aligning with the dashboard's access pattern. At scale, storage capacity is cheap, but compute cycles are expensive. Deliberately duplicating data is the necessary cost to optimize for diametrically opposed access patterns. Looking at this complete architecture map, you can see how all the individual components lock together: the microservices, the multi-tier cache, sharded databases, and async background workers. The right path takes user input, generates a mathematically guaranteed unique ID from a Snowflake node, converts it to base 62, and stores it, avoiding database collisions entirely. The read path hits the high-speed cache, drops an analytics packet into the Kafka queue, and executes a 302 redirect instantly, without waiting for the database to write the click. Every component introduced here serves a singular engineering mandate: protect the latency of the critical read path at all costs. Scaling a distributed system to this magnitude requires identifying individual bottlenecks and applying the structural discipline to decouple them.